Hey, physics kids, this is Mr. Gloria. How are y'all doing today? Hope you're doing pretty well. I'm putting together our Unit 11. Our Unit 11 involves a type of motion we really haven't discussed yet, and that's a circular motion. We do a lot of circular motions here on our planet when we're driving our car, maybe going through some of the roundabouts in our area, orbits of planets, solar systems, going around the galaxy. There's a lot of types of circular motion, and that's kind of what this week's unit is all about. And circular motion kind of has a special name. It's called centripetal, and that just means center seeking, and we're basically looking at special types of forces that can constrain an object to move in a circle, and I'll talk about that a little bit here. What we've been talking about, velocity, acceleration, forces, we've been talking about what's called linear motion kind of along a line. The circular motion is, again, a little bit different, right? So we'd like to maybe through this unit ask and answer, the following questions. What keeps objects moving in circles? What maintains circular motion, and how do objects even maybe start moving in circular paths? And again, we're saying that we have these kind of special forces that constrain objects to move in a circle. We call these forces centripetal forces. Centripetal is just kind of a fancy word that means towards the center. So for example, if we have this maybe ball on this rope or this string, and we're rotating it around, we're maintaining circular motion. But I have to basically exert an inward force on that string to keep that object, to keep that ball moving in a circle. So that's what I mean then by F sub c, a centripetal force. So that force is directed inward. And notice that the ball also has this velocity. This velocity then is another vector. So we have these two vectors that are acting on this object moving in a circle. We have a force vector, again we call that the centripetal force, and we have the velocity. We're going to call that the tangential velocity. And these two vectors working together then constrain that object. I don't know if you know what that word means, constrain. It keeps that object moving in a circular path. So basically, first off, what are centripetal forces? These are forces that act inward towards the center of the circle. Keeps the object moving in that circle. In combination with this force, we have this forward velocity. We call that the tangential velocity. Okay, so there's my picture again. There's my centripetal force, and there's my tangential velocity. Now, we call this a tangential velocity. It's just a forward velocity, but it's always tangential to the circular path. Tangential means basically it hugs that line and goes forward. Notice that these two vectors in circular motion are always at right angles, or they're perpendicular to each other. Now, this unit can get fairly mathematical, but I'm going to treat it more conceptually. There will be a few practice problems that you'll have to work on, and there'll be a few problems on the quiz or assessment, but most of this unit will be more conceptual. There is a couple of new equations. This first one is called the centripetal force equation. So that this Fc, this centripetal force, to keep that object constrained in a circle, can be calculated with this equation, and that M stands for mass. So for example, if my object is heavier, it's going to take me more force, more tug to keep that object on that string. Okay, so that M is the mass of the object in kilograms. Again, this is a metric equation, and we have to use metric units. So the F, the centripetal force, is in newtons. So we have to multiply the mass of the object. And that kind of makes sense, doesn't it, kids? If something is heavier or lighter, it would take a different amount of force. If I have this ball on this string and I'm rotating it around and around, that ball is heavier, it's going to take me more force. Well, if I rotate it at a different speed, it's also going to impact that force, or it's going to change that force. If I'm trying to rotate it faster and faster, it's going to take more force on my arm to pull that kind of inward. It turns out, though, that velocity, that tangential velocity, we're going to measure that again in meters per second, but it turns out that we have to kind of square that in my equation. And then we divide that by the radius of the circle, and again, this is going to be in meters. That's our preferred unit there. So if the radius is small, then it's going to increase my force. See, it's in the denominator. If the radius is larger, it's going to make my force less. So doesn't it make sense these three variables are important, really, when we talk about then motion along a circle? The mass of the object, its velocity, and the radius. This is again called the centripetal force equation. Now let me add a little bit more to that. Now, this centripetal force is unbalanced. We said then when we're dealing with unbalanced forces, we can incorporate then Newton's second law, right? So we said if we have CV, then all my forces are balanced. If I have CA of some sort, then I have an unbalanced scenario and I have an acceleration. That's what we have really here with this centripetal force. It's unbalanced. See, there's nothing balancing that force out. So we use then the net force is equal to ma. That's Newton's second law. Okay, and because we have an unbalanced force, we're going to have then an acceleration. Okay, and we call that the centripetal acceleration. So if we say F equals ma, then that A part is just this part right here. Okay, it's just this part right here of this centripetal force equation. We can think about this A also. We said that acceleration is produced when we have a change of velocity with respect to time. And our velocity, even though the quantity of my speed or velocity might stay the same, I'm constantly changing the direction of that vector. If I'm changing the direction of that vector, then at every instant of time, then I have to have then a vector or an acceleration. My speed may be the same. I may be rotating this at so many meters per second. That may not change, but because of my directional change, then I have an acceleration present. I'm changing the direction of my vector. There's also another useful equation that you might find helpful here, and I think you probably will, but when we have an object in a circle, then we can, if that speed is constant, then we can take its circumference over the time that it takes. So we can get that velocity in that circle, that'd be the tangential velocity, by taking its circumference, 2 pi r. Then that would be distance, 2 pi r, the circumference of a circle, over the time. And this time typically is given a special name. It's called the period, which would be like the period of how much time it takes in seconds to go around. Let me kind of show you this video that I kind of made. Let me do that real quick. Let me set this video up. I basically have this turntable. This is an old record player, and I put this turntable at a specific, what's called rotational speed. And I've got these 3 different colors of clay balls, and I use clay, just little spheres of clay, because I could stick them down on the record. So let me show you this video real quick. Okay, so basically I have all 3 of these clay balls. I've got a red one, a blue one, and a yellow one. They're all traveling at the same rotational speed. So it takes the same amount of time for each one to make one then rotation, or one orbit, you might say. All right, let me keep playing it. However, the red one here is closer to the spindle, or the axis of rotation. It has a small radius. So it doesn't have as much circumference to go around as the blue or yellow one. The yellow one's at the largest radius. It's got the greatest circumference. So it actually is traveling at a faster velocity or tangential speed than the red one or the blue one. All right, does that kind of make sense? That's another reason why this is a little bit confusing. We can have the same objects. These same objects are traveling at the same rotational speed, but they have different tangential or linear speeds because of different radii or different circumferences. Okay, let me kind of end that there. So objects at a larger radius have to travel further around. That distance is going to be larger. All right, so velocity is also kind of velocity of the linear tangential velocity the object have. We can kind of relate it also to the circumference. Okay, so let me just kind of wrap this up and let me just kind of repeat myself here a little bit. So we've got two vectors acting simultaneously, and those two vectors are at right angles with each other. The force vector acts inward. We call that the centripetal force. The velocity acts forward. We call that the tangential velocity. There's 90 degrees between these two vectors when we have circular motion. We need both of these to act at the same time, simultaneously. Okay, it's a kind of a combination or a mix of these two vectors. Now, what might happen then? What might really happen if the string breaks? Well, if I'm rotating this around and the string breaks, then I get rid of that force. Now all we have is a tangential velocity vector and the object flies forward. All right. What would happen though, maybe if we decrease the velocity? Well, this happens kind of with satellites as they kind of orbit our planet, that as a satellite impinges on some of the air molecules in the upper atmosphere, its velocity gets less and less. Well, its velocity, if it gets less and less, there's really not enough maybe velocity to keep it in a specific orbit that high. So this is called a decaying orbit, and eventually then the gravity or the centripetal force of our planet then will pull that satellite in. So again, we need two things. We need two vectors working together, and they have to be working together kind of properly. We have the tangential or forward velocity, and we have then the centripetal or inward force. Now, what are some of the forces that can act centripetally? Well, they're not any really new forces. We kind of know these forces because we've studied them in a previous unit. So we could have tension in a string. That's the pull of a cable or a rope or a string. Okay, that could act to keep this object in a circle. Gravity from maybe the sun or a planet can act to keep then satellites or a moon or the planets in orbit. In airplanes, we have then a force called lift, and we can have airplanes kind of move in circles. Friction in a car can keep an object like this car. So this would be friction between the tires and the road can act inward and constrain that car to move in a roundabout or in a curve. We've got basically the normal force and weight, which can act, like in a roller coaster, for example. If these cars aren't traveling fast enough, if this V is not big enough, then everything's going to fall towards the center. All right. So that's kind of what this unit's all about. And again, there'll be some notes to take over some websites. And there'll be some then assignments to complete. Hey, we'll talk to you later, kids. Bye.